1944, somewhere over the Pacific near Rabaul. Luftwaffe intelligence officer Hauptmann Ernst Richter sat in a cramped interrogation room at Stalag Luft 3, studying captured American technical documents that had arrived from the Eastern Front. His assignment was simple: analyze enemy aircraft capabilities, identify weaknesses, prepare countermeasures. But the numbers in front of him made no sense whatsoever. American fighter aircraft were achieving speeds and climb rates that violated every principle of aeronautical engineering he had learned at the Technical University of Berlin. The Republic P-47 Thunderbolt, a massive aircraft weighing over 6 tons, somehow climbed at nearly 4,000 feet per minute. The North American P-51 Mustang routinely exceeded 450 miles per hour in level flight. And now, intelligence reports from the Pacific spoke of a new American fighter called the F4U Corsair that was decimating Japanese air forces with performance figures that seemed physically impossible. Richter checked the documents again. The Corsair used the same Pratt & Whitney R2800 engine as the Thunderbolt, 18 cylinders, 2,000 horsepower. Good numbers, but not exceptional. German engines produced similar power. The Focke-Wulf 190 and the Messerschmitt Bf 109 both had excellent performances. Yet somehow, the American aircraft were consistently faster, could climb higher, and maintained power at altitudes where German fighters gasped for air. There had to be an explanation. Engine design? No, German engineering was superb. Aerodynamics? Perhaps, but not enough to account for such dramatic differences. Weight? The Americans built heavy fighters, not light ones. Richter had interrogated dozens of captured Allied pilots. They spoke casually of pushing their throttles forward, of emergency war power settings, of manifold pressures that would tear a German engine apart within minutes. The American pilots mentioned something else too, something that Richter initially dismissed as pilot bravado or propaganda. They spoke of their fuel as if it were a secret weapon. One captured P-51 pilot had laughed when asked about German fighters trying to catch him. "You can't chase what you can't catch," he had said. "We're flying on 130 octane. What are you running? 87? Richter had not understood the significance of that statement. Not then. Not until the documents in front of him revealed a truth that German intelligence had somehow missed for years. The Americans were not just building better aircraft. They were fueling them with a substance that transformed ordinary engines into powerhouses that German technology could not match. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The year 1943 marked the turning point of the Second World War in multiple theatres. In Europe, the Wehrmacht had been defeated at Stalingrad. In North Africa, Axis forces had surrendered. In the Pacific, American forces had secured Guadalcanal and were beginning their island-hopping campaign toward Japan. But beneath these military victories lay a more fundamental shift that few people understood at the time. Germany had entered the war with significant technological advantages. The Luftwaffe fielded experienced pilots flying capable aircraft. The Messerschmitt Bf 109 had performed excellently in Spain, Poland, France, and during the Battle of Britain. German engines used direct fuel injection, which allowed pilots to perform negative G maneuvers without the engine cutting out a critical advantage in dogfights. German synthetic fuel production, developed through the Bergius process and Fischer-Tropsch method, had freed the Reich from dependence on imported petroleum. Nazi propaganda celebrated German engineering as the finest in the world. Posters showed Luftwaffe pilots as modern knights, defending the fatherland with superior technology and unmatched skill. Every factory worker, every school child, believed that German science and German discipline would overcome any material disadvantage. The regime had built this belief carefully, systematically, over years of indoctrination. But by 1943, the Luftwaffe was encountering a problem that propaganda could not explain away. American fighters were arriving over Europe in growing numbers, and they were performing in ways that violated German expectations. Intelligence reports spoke of P-47 Thunderbolts flying escort missions to targets deep inside Germany, somehow maintaining formation at altitudes where Luftwaffe fighters struggled to operate. P-51 Mustangs appeared over Berlin itself, having flown hundreds of miles from bases in England, with enough fuel remaining to engage in combat. In the Pacific theater, an even more disturbing pattern emerged. The United States Navy and Marines had introduced a fighter called the F4U Corsair. Japanese intelligence reports, captured by German forces, described an aircraft that dominated every aspect of aerial combat. The Corsair could outrun, outclimb, and outdive the Mitsubishi A6M0, previously considered one of the finest fighters in the world. American pilots flying Corsairs achieved kill ratios of 11-1 against Japanese aircraft. Entire squadrons of experienced Japanese aviators simply disappeared from the sky. German technical intelligence officers studied these reports with growing concern. They analyzed captured American aircraft when possible, measuring every dimension, weighing every component, testing every system. The airframes were well designed, but not revolutionary. The engines were powerful, but fell within the parameters of existing technology. The armament was heavy 650 caliber machine guns on most fighters, but firepower alone could not explain the Cullinan performance advantage. What the Germans failed to recognize, what their intelligence apparatus completely missed, was that the Americans had solved a problem that German chemists and engineers had struggled with for decades. They had developed a way to produce aviation gasoline with octane ratings far beyond what Germany could achieve. And that difference, a seemingly minor variation in fuel chemistry, was determining the outcome of air battles across the globe. Ernst Richter had joined the Luftwaffe in 1938, fresh from the Technical University of Berlin with a degree in mechanical engineering. He had not trained as a pilot. His skills lay in analysis, in understanding the intricate systems that made aircraft function. The Luftwaffe needed men who could evaluate enemy technology, identify vulnerabilities, and recommend countermeasures. Richter had excelled at this work. By 1942, he had been promoted to Hauptmann and assigned to intelligence analysis at Luftwaffe headquarters. His job was to read interrogation reports from captured enemy pilots, study technical documents recovered from crash sites, and piece together an accurate picture of Allied aviation capabilities. It was meticulous, unglamorous work, but it was essential. The documents crossing his desk in 1943 told a consistent story. American aircraft performance had improved dramatically since the beginning of the war. In 1940, American fighters had been unremarkable, adequate, but not exceptional. The Curtiss P-40 Warhawk had reasonable speed but poor high-altitude performance. The Bell P-39 Era Cobra had a unique engine configuration but suffered from limited range and mediocre climb rate. By 1943, everything had changed. The P-47 Thunderbolt, a massive fighter weighing over 13,000 pounds when fully loaded, somehow combined speed, altitude performance, and firepower in ways that seemed impossible. The P-51 Mustang, initially designed with an American engine, had been transformed by the addition of the British Rolls-Royce Merlin engine into perhaps the finest long-range fighter in the world. And in the Pacific, the Corsair was rewriting the rules of naval aviation. Marine pilots flying from land bases in the Solomon Islands were achieving air superiority against Japanese forces that had dominated the region for 2 years. The Corsair could carry twice the bomb load of earlier American fighters, while still maintaining performance that exceeded most purpose-built interceptors. Richter knew these facts. What he did not know was why. He had studied aeronautics. He understood propeller efficiency, wing loading, drag coefficients, engine compression ratios. The American advantage could not be explained by superior design alone. There had to be another factor, something that German intelligence had overlooked or failed to recognize as significant. The breakthrough came in late 1943, when Richter interrogated a captured B-17 pilot who had been shot down over Germany. The pilot was a lieutenant from Ohio, 23 years old, educated at a state university. He had been flying combat missions for 4 months before his aircraft sustained fatal damage from anti-aircraft fire. His crew had bailed out, and most had been captured. The interrogation was routine. Richter asked about formations, tactics, navigation methods, target selection. The pilot answered carefully, providing only information that was already publicly known. But toward the end of the session, Richter asked a question about fuel consumption. How long could a B-17 remain airborne? What was the maximum range? The pilot laughed. Depends on what fuel you're burning. We're using 100 octane now, sometimes 130 for the fighters. Back home, our trainers still run on 87. Makes a hell of a difference in performance. Richter stopped writing. 130 octane? 4. Fighters, yeah. The P-51 seconds and P-47 seconds run it. Let them push the engines harder, especially at altitude. I don't know the technical details, I'm not an engineer, but our crew chief explained it once. Higher octane means you can run higher manifold pressure without detonation. More boost equals more power. After the interrogation ended, Richter returned to his office and pulled every technical report related to American aviation fuel. He had seen references to octane ratings before, but had not understood their significance. Germany produced 2 primary aviation fuel grades, B4, which had an octane rating of 87/95, and C3, which reached 91/100. These numbers referred to lean mixture and rich mixture ratings, a measure of the fuel's resistance to premature detonation under different engine operating conditions. The captured documents indicated that American fighters were using fuel with ratings of 100/130, and in some cases, 115/145. The British were testing even higher grades. This meant that American and British pilots could operate their engines at manifold pressures that would cause German engines to destroy themselves through detonation. Richter understood the implications immediately. An engine's power output was directly related to the amount of air and fuel it could combust in each cylinder. Higher manifold pressure meant more air could be forced into the combustion chamber, which meant more fuel could be burned, which meant more power could be generated. But increasing manifold pressure also increased the risk of detonation, the premature, uncontrolled explosion of the fuel-air mixture that could blow holes through pistons and destroy engines within seconds. Higher octane fuel resisted detonation. It allowed engines to operate at higher compression ratios and higher boost pressures without the fuel exploding prematurely. This meant that American fighters could extract significantly more power from engines that were, on paper, similar in displacement and design to German engines. The numbers were devastating. A Packard Merlin engine running on 130 octane fuel could produce over 1,800 horsepower at military power settings, with emergency war power reaching over 2,000 horsepower. The same basic engine design, running on German C3 fuel, would be limited to approximately 1,300 horsepower to avoid catastrophic detonation. Richter drafted a report. He outlined the fuel disparity, explained its tactical implications, and recommended immediate research into advanced fuel production methods. The report went up through channels to Luftwaffe Command, and there it died, buried under more pressing concerns about pilot training, aircraft production, and the crushing reality of fighting a multi-front war against enemies with seemingly unlimited resources. The F4U Corsair had first flown in May 1940. It was designed by the Vought Corporation in response to a US Navy requirement for a carrier-based fighter with exceptional performance. The Navy wanted speed, firepower, and the ability to operate from aircraft carriers. Vaught's design team, led by Rex Beisel, created an aircraft around the most powerful engine available, the Pratt & Whitney R-2800 double Wasp. The R-2800 was a radial engine with 18 cylinders arranged in 2 rows. It produced 2,000 horsepower, an enormous output for the time. But such a powerful engine required a large propeller to absorb all that power and convert it into thrust. Vought fitted the Corsair with a propeller over 13 feet in diameter, the largest ever mounted on a fighter aircraft. This created a problem. The propeller needed sufficient ground clearance during takeoff and landing. Conventional straight wings would require impossibly long landing gear to lift the aircraft high enough off the ground. Vaught's solution was innovative: inverted gull wings. The wings angled downward from the fuselage, then bent upward at the point where the landing gear attached. This allowed relatively short, sturdy landing gear while maintaining adequate propeller clearance. The design worked. When the prototype Corsair flew in October 1940, it exceeded 400 miles per hour faster than any American fighter then in service. It climbed at nearly 3,000 feet per minute. It could carry a substantial payload of bombs or rockets while maintaining fighter performance. The Navy ordered the aircraft into production immediately, but carrier operations proved problematic. The Corsair's long nose blocked the pilot's forward vision during landing approaches. The aircraft tended to bounce when the wheels touched the deck. Most critically, it had a tendency to stall unexpectedly on the port wing during low-speed flight, which could be fatal during carrier landings. The Navy decided to deploy the Corsair primarily with Marine Corps squadrons operating from land bases, where these characteristics were less critical. Marine pilots embraced the Corsair enthusiastically. In February 1943, VMF 124 became the first squadron to fly the Corsair in combat, operating from Henderson Field on Guadalcanal. Within weeks, it became clear that the Corsair was superior to every Japanese fighter in the theatre. It was faster than the Zero, climbed better than the Zero, dived better than the Zero, and could absorb battle damage that would destroy lighter aircraft. The only advantage the Zero retained was maneuverability at low speeds. Japanese pilots, trained in tight-turning dogfights, initially attempted to engage Corsairs in close-quarters combat. American pilots quickly developed tactics that negated this advantage. They would use their superior speed to make high-speed passes, fire their 650 caliber machine guns, then climb away before Japanese pilots could maneuver into position. Boom and zoom tactics replaced turning dogfights, and Japanese aircraft fell from the sky in droves. By mid-1943, Marine squadrons in the South Pacific were flying Corsairs almost exclusively. VMF 214, commanded by Major Gregory "Pappy" Boyington, became legendary. In just 84 days of combat operations, the squadron claimed 97 enemy aircraft destroyed and damaged over 100 others. Boyington himself shot down 28 Japanese aircraft before being shot down and captured in January 1944. The Corsair's success in the Pacific theatre was absolute. Japanese forces, which had begun the war with experienced pilots and capable aircraft, found themselves unable to contest American air superiority. By late 1943, seasoned Japanese aviators were being systematically eliminated, and their replacements had neither the training nor the equipment to compete effectively. The Corsair achieved an overall kill ratio of 11 enemy aircraft destroyed for every Corsair lost in aerial combat. What made this dominance possible was not just the Corsair's design, though the design was excellent. It was the combination of airframe, engine, tactics, and most critically fuel. The Corsair's R-2800 engine, running on American 100-octane and later 130-octane fuel, could produce power outputs that Japanese engines could not match. At critical moments in combat, American pilots could push their throttles forward, engage water injection for emergency power, and accelerate away from danger or pursue fleeing enemy aircraft with a performance advantage that decided battles before they truly began. German intelligence received reports about Corsair performance from Japanese sources. The Axis powers shared technical information, though not always completely or quickly. By 1944, German analysts knew that American fighters in the Pacific were dominating Japanese forces. They knew about the Corsair's specifications: wingspan, length, empty weight, maximum weight, armament, top speed, service ceiling, They knew it used the R2800 engine. What they did not know, what they failed to understand until too late, was that the Americans had made a fundamental breakthrough in fuel technology. They had industrialized the production of high-octane aviation gasoline on a scale that Germany could not match. By 1944, American refineries were producing hundreds of thousands of barrels of 100-octane fuel daily. Specialized facilities were manufacturing 115-octane and even experimental 150-octane fuels for fighter aircraft operating in critical theaters. Germany, meanwhile, struggled to produce even its standard C3 fuel in sufficient quantities. The synthetic fuel plants that converted coal into gasoline were complex, expensive, and vulnerable to bombing. Romanian oil fields provided some natural petroleum, but not enough to meet military needs. German fuel production peaked in early 1944 at approximately 124,000 barrels per day of all fuel types combined. American production of high-octane aviation fuel alone exceeded that figure by a substantial margin. The disparity was not just quantitative, it was qualitative. German engineers understood the chemistry of octane production. They knew how to produce higher-grade fuels using aromatic hydrocarbons like benzene, toluene, and xylene. They knew about tetraethyl lead additives that could boost octane ratings. The knowledge existed. What Germany lacked was industrial capacity. Producing high-octane fuel required sophisticated refining equipment, abundant petroleum feedstock or coal, chemical processing plants for additives, and most critically time and resources that Germany did not have. By 1943, Germany was fighting on multiple fronts. Its industrial capacity stretched to the breaking point, its fuel supplies targeted by Allied bombing campaigns. Every litre of aviation fuel had to be extracted from coal through energy-intensive processes that consumed resources desperately needed elsewhere. The Americans, by contrast, had petroleum in abundance. Texas, Oklahoma, California, vast oil fields that had been producing crude oil for decades. They had refineries with modern cracking towers and distillation columns. They had chemical plants producing tetraethyl lead and other additives on an industrial scale. Most importantly, they had no enemy bombers overhead destroying their production facilities. Ernst Richter understood this asymmetry intellectually. He could read production figures, calculate fuel consumption rates, and project future shortages. What he could not grasp, what no amount of technical analysis could convey, was the psychological impact this disparity would have on German personnel once they experienced American abundance directly. That lesson came not from reports or calculations, but from the testimony of German prisoners of war who had been captured and shipped to camps in the United States. In the spring of 1944, Germany established a program to debrief prisoners of war who had been repatriated through neutral countries or escaped from Allied captivity. The goal was to gather intelligence about Allied industrial capacity, military capabilities, and civilian morale. What the program discovered was not what the German command had hoped to hear. Obergefreiter Hans Keller had been captured in North Africa in May 1943. He was a tank crewman, 24 years old, from a farming family in Bavaria. After his capture by British forces, he had been shipped to a prisoner of war camp in the United States, first to Virginia, then to a work camp in Nebraska. He spent 15 months in American captivity before being repatriated through a prisoner exchange program in late 1944. His debriefing officer asked standard questions about camp conditions, security measures, prisoner morale, and evidence of war weariness among Americans. Keller answered mechanically at first. Yes, the camps were adequately supplied. Yes, security was strict but not brutal. Yes, prisoners worked on farms to alleviate labor shortages caused by American men serving overseas. Then the officer asked about American industrial capacity. What had Keller observed? What evidence was there of material shortages? Keller was silent for a long moment. Then he said, "There are no shortages. None. We were fed better as prisoners than I ate at home before the war. The guards' uniforms were new. The trucks that transported us were new. The farms where we worked had machinery I had never seen before, mechanical harvesters, tractors everywhere, equipment that would cost a fortune in Germany, and American farmers had it lying in their fields like it was nothing special. The debriefing officer pressed for specifics. What about rationing? Surely American civilians experienced rationing of food, gasoline, rubber, consumer goods? They complained about rationing, Keller said. I heard civilians in town complaining when we passed through, but their rationing was more than we had in Germany before rationing even began. I saw grocery stores with shelves full of food. I saw automobile dealerships with dozens of cars. I saw children throwing away food we would have been grateful to eat. The Americans do not understand what scarcity means. They have never experienced it. These reports troubled German intelligence analysts, but they were often dismissed as exaggeration or as the biased observations of men who had been subjected to propaganda. Prisoners might have been shown only well-supplied areas to demoralize them. Their perceptions might have been warped by captivity and isolation from accurate information about the war's progress. But the reports kept coming, and they were remarkably consistent. Every prisoner who returned from American captivity told the same story. America was not merely producing enough to supply its military, it was producing such abundance that prisoners of war enemy soldiers were living better than German civilians at home. Medical supplies, food, clothing, machinery, consumer goods, all existed in quantities that Germans could not comprehend. Dr. Friedrich Weber was a Luftwaffe flight surgeon, 36 years old, captured in Italy in 1943. He was educated at Heidelberg, trained in the finest German medical traditions, and a skilled surgeon who had performed hundreds of operations under field conditions. After his capture, he was sent to a prisoner of war camp in Kentucky, where he worked in the camp hospital treating fellow prisoners. His debriefing in 1944 focused on medical supplies. What medicines were available? What surgical equipment? How were serious cases handled? Weber's answer was devastating in its simplicity. They had everything. Penicillin, which we had only heard about, sterile bandages in unlimited quantities, morphine for every patient who needed it, plasma for transfusions, surgical instruments that were sharp and didn't need to be sharpened repeatedly until they bent. They had supplies sitting unused in storage closets that would have saved hundreds of lives in our field hospitals. The debriefing officer asked if this might have been special provision for prisoners, part of propaganda efforts. No, Weber said. I saw the civilian hospitals. I saw the supply trucks delivering materials. This was normal for them. They produced medical supplies the way we produced shells and bullets in vast industrial quantities. And they could do this while also supplying their military, while also supplying the British and Russians under Lend-Lease. We cannot compete with this. It is not possible. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The reports from returned prisoners created an uncomfortable reality for German leadership. For years, propaganda had told the German people that they were fighting a decadent, weak enemy. America was portrayed as a nation of jazz musicians and Hollywood actors, undisciplined and soft, incapable of the sacrifice necessary for total war. The Soviet Union was depicted as primitive and backwards, armed with obsolete equipment and driven only by communist fanaticism. Britain was exhausted, clinging to past glory, surviving only through the charity of its American patrons. These narratives had served an important purpose. They maintained morale. They justified continued sacrifice. They explained away defeats as temporary setbacks against enemies who relied on numbers rather than quality. But the returning prisoners told a different story, and it was impossible to completely suppress. America was not weak. It was terrifyingly strong. Its industrial capacity was not just superior to Germany's, it was operating at a level that made comparison meaningless. American factories were producing aircraft at rates of thousands per month. American shipyards were launching cargo vessels faster than U-boats could sink them. American oil fields were pumping petroleum that was refined into aviation fuel that gave American pilots a performance advantage that no amount of German skill or courage could overcome. By late 1944, even Luftwaffe pilots who had never been captured understood that something fundamental had changed. The skies over Germany, which had once been contested with roughly equal losses on both sides, had become shooting galleries where American fighters operated with near impunity. The massive formations of B-17 and B-24 bombers, once vulnerable to determined fighter attacks, now flew with escorts of P-51 Mustangs that could accompany them, all the way to targets deep inside the Reich and back to England. German pilots were not cowards, they were not incompetent. Many were extraordinarily skilled, veterans of years of combat, who understood tactics and gunnery as well as any aviator in the world. But skill had limits, courage had limits. When an American P-51 could accelerate away from a pursuing 00-190, when a P-47 could climb to altitudes where German fighters struggled to operate, when squadrons of Corsairs in the Pacific could maintain continuous combat air patrols that made Japanese operations impossible. These were not victories of skill, they were victories of chemistry, of industrial capacity, of fuel technology that Germany could not match. The science behind octane ratings was well understood by chemists in both Germany and America. Octane rating measured a fuel's resistance to detonation premature, uncontrolled combustion that could destroy engines. Pure iso-octane, a specific hydrocarbon molecule, was assigned a rating of 100. Fuels that resisted detonation better than pure iso-octane were given performance numbers above 100, not because they contained more than 100% iso-octane, which would be chemically impossible, but because they performed better on standardized engine tests than pure iso-octane would. To produce high-octane fuel, refiners used several methods. Catalytic cracking broke down large hydrocarbon molecules into smaller, more useful ones. Alkylation combines smaller molecules into larger, high-octane compounds. Polymerization linked unsaturated hydrocarbons into branched molecules that resisted detonation. Reforming rearranged molecular structures to create more desirable combustion characteristics. These processes required specialized equipment, reactors, catalysts, distillation towers, chemical separators. They required feedstock, either petroleum or coal. They required energy heat, pressure, electrical power, and they required additives, primarily tetraethyl lead, which could boost octane ratings by several points per gram of lead added to each gallon of fuel. American refineries had been producing high-octane fuel since the 1930s. Companies like Standard Oil, Shell, and Texaco had invested heavily in refining technology. By 1941, when America entered the war, its petroleum industry could produce 100-octane fuel in substantial quantities. By 1943, production had expanded to meet military needs completely, with enough surplus to supply British forces under Lend-Lease arrangements. British refiners, working with American technology and American-supplied crude oil, had developed even higher grades. By mid-1944, Royal Air Force fighter squadrons were using 150-octane fuel, technically rated as 100/150, indicating lean and rich mixture performance numbers. This allowed British Merlin engines and American R-2800 engines to operate at boost pressures, approaching 72 inches of mercury, generating power outputs that would have been impossible with lower-grade fuels. Germany's fuel situation was entirely different. Without access to abundant petroleum, Germany had built its fuel industry around coal conversion. The Burgess process and Fischer-Tropsch synthesis could transform coal into liquid fuels. But these processes were complex, expensive, and produced fuel with relatively low octane ratings. German B4 fuel, the standard aviation gasoline, had a lean mixture octane of 87 and a rich mixture rating of 95. C3 fuel, used in fighters, reached 91 lean and 100 rich. These were adequate ratings for engines designed to use them. German engines were built with compression ratios and boost pressures matched to available fuel. Everything worked as a coordinated system. The problem was that this system could not compete with what the Allies had developed. When a Luftwaffe pilot pushed his throttle to emergency power, he might reach 60 inches of mercury manifold pressure for brief periods, generating perhaps 1,700 horsepower from his engine. When an American pilot pushed his throttle forward, he could reach 67 inches, or even 72 inches with water injection, generating over 2,000 horsepower. That 500 horsepower difference translated directly into speed, climb rate, acceleration, all the performance characteristics that determined who won and who died in aerial combat. By early 1945, Ernst Richter had compiled extensive documentation about the fuel disparity. He had interrogation transcripts, he had technical reports, he had calculations showing exactly how much performance advantage American and British fighters gained from their superior fuel. He had recommendations for crash programs to increase German octane production. None of it mattered. Germany's synthetic fuel industry was collapsing under sustained Allied bombing. The complex hydrogenation plants that converted coal into gasoline were vulnerable to precision attacks. When key facilities were destroyed, months or years of production capacity disappeared. Romanian oil fields had been captured by Soviet forces. What little high-grade fuel Germany could produce was being hoarded for the new jet fighters, Messerschmitt 262s and Arado 234s that represented Germany's last hope for contesting Allied air superiority. The Luftwaffe pilots who remained those who had survived years of combat, those who had the skill and experience to potentially compete with Allied pilots, found themselves grounded for lack of fuel. Training for new pilots had been reduced to dangerous minimums. Where American pilots received 300 to 400 hours of flight training before their first combat mission, German pilots were being rushed into battle with fewer than 150 hours. Many had never fired their guns at a moving target. Many had barely mastered formation flying. And when these undertrained pilots did engage Allied fighters, they faced aircraft that had performance advantages built into every system, the fuel that powered Allied engines, the abundant ammunition that filled their guns, the replacement aircraft that arrived within days when losses occurred, the maintenance supplies that kept equipment operational, the confidence that came from knowing that every aspect of material support favored Allied pilots. The Corsair in the Pacific represented all of this in condensed form. It was not just an aircraft. It was a symbol of American industrial might. Every Corsair that flew combat missions was a testament to petroleum refineries in Texas and California, to chemical plants producing tetraethyl lead and other additives, to factories stamping out airframe components, to assembly lines where workers, many of them women, riveted sections together with precision that German forced labor could never match, to supply ships that crossed the Pacific carrying spare parts, ammunition, fuel, food, everything that modern warfare required. When Marine pilots flew Corsairs from primitive airstrips in the Solomon Islands, they were supported by a logistics system that stretched back 8,000 miles to the continental United States. Spare engines arrived within weeks. Damaged aircraft were repaired or replaced. Fuel came in tankers that Japanese submarines could no longer interdict effectively. The entire system worked because America had the industrial capacity to make it work, and that capacity was fundamentally enabled by energy, by petroleum, by coal, by hydroelectric power, by the raw materials that America possessed in abundance, and Germany desperately lacked. Ernst Richter understood this by the war's end. He understood that Germany had lost not because its soldiers lacked courage, not because its equipment was inherently inferior, not even because its strategy was flawed, though it was. Germany lost because it could not match Allied industrial production, and at the heart of that production disparity was energy, oil, coal, electricity, the basic inputs that powered modern economies and modern militaries. The Americans had not just outproduced Germany. They had done so while simultaneously supplying Britain, the Soviet Union, and other allies through Lend-Lease. They had done so while maintaining civilian living standards that exceeded German pre-war prosperity. They had done so with such efficiency that prisoners of war enemy soldiers lived better in American camps than German civilians at home. This was not a difference of degree. It was a difference of kind. It was the difference between an industrial economy that had fully mobilized for total war and could still meet every demand placed upon it, and an economy that had stretched itself to the breaking point and was now shattering under pressure it could not withstand. The reports from German POWs returned from America conveyed this reality more effectively than any technical analysis could. Hans Keller, the tank crewman from Bavaria, told his debriefing officer about working on Nebraska farms where the machinery was newer and more advanced than anything he had seen in Germany before the war. He described warehouses full of spare parts for equipment that was still in use. He described supermarkets with more food than entire German towns could access. He described seeing American housewives throw away meat that German families would have considered a luxury. Dr. Friedrich Weber, the flight surgeon, described medical facilities that would have been considered excellent by peacetime standards, available in a prisoner of war camp in rural Kentucky. He described watching American doctors discard bandages after single use, something German field hospitals had been unable to do since 1942. He described penicillin distributed so freely that even minor infections received treatment, while German hospitals were rationing the drug for only the most critical cases if they had any at all. These stories spread through debriefing centers, through military units, through the civilian population. They could not be completely suppressed because too many men had experienced the same reality. And what they conveyed was more demoralizing than any military defeat, the understanding that Germany had never stood a realistic chance of winning. The war had been decided not on battlefields, but in refineries, factories, mines, and farms. In the unglamorous work of industrial production that determined which nation could field more aircraft, more tanks, more ships, more of everything that modern warfare demanded. The F4U Corsair, flying over the Pacific, achieving its 11-to-1 kill ratio against Japanese forces, was powered by fuel that represented all of this. Every gallon of 130-octane aviation gasoline carried in the Corsairs' tanks was a product of American petroleum infrastructure, of refining technology developed through decades of commercial competition, of chemical additives produced on industrial scales, of a supply chain that stretched from oil wells in Texas to fighter aircraft operating thousands of miles from home. German intelligence had documented American aircraft specifications. They knew the Corsair's wingspan, its empty weight, its armament, and its top speed. They could calculate its rate of climb, its service ceiling, its combat radius. What they could not quantify was the industrial system that produced it, maintained it, fueled it, and made it effective. That system was so far beyond German capacity by 1944 that comparison became meaningless. And the ultimate irony, the bitter truth that men like Ernst Richter understood too late, was that Germany had possessed the scientific knowledge to produce high-octane fuel. German chemists understood catalytic cracking and alkylation. German engineers could design the necessary refining equipment. What Germany lacked was not knowledge. It lacked oil fields and the time and resources to build the infrastructure that American companies had constructed over decades. The war had been lost before the first shot was fired. It had been lost in decisions made in the 1920s and 1930s about how to organize economies, what resources to develop, what industries to support. It had been lost when Germany chose autarky and synthetic fuels over international trade and resource access. It had been lost when American companies invested in refining technology, while German industry focused on immediate production over long-term capacity building. By the time Luftwaffe pilots were encountering P-51 Mustangs over Berlin, by the time Marine pilots were flying Corsairs with impunity over Japanese-held islands, the war's outcome had been determined for years. The fuel in American tanks had decided it. The aluminum in American airframes had decided it. The food in American mess halls had decided it. All of it enabled by industrial capacity that Germany simply could not match. Ernst Richter survived the war. In the chaos of Germany's collapse, He was captured by American forces and spent 6 months in a prisoner of war camp before being released. The camp was in southern Germany, hastily constructed, crowded, far from the comfortable facilities that early war prisoners in America had experienced. Rations were minimal. But even under these conditions, Richter noticed things that confirmed everything the returned prisoners had reported. The American Guards' uniforms were clean and in good repair. Their vehicles, trucks, jeeps, staff cars were numerous and well maintained. The supply convoys that passed the camp carried more materiel than entire German divisions had possessed at the war's beginning. America had won, and won so completely that its forces could occupy a defeated nation while still appearing fresh, well-supplied, effortlessly superior. After his release, Richter returned to Berlin, or what remained of it. He walked through ruins that Allied bombing had created. He saw factories reduced to rubble. He saw synthetic fuel plants destroyed beyond repair. He saw the physical evidence of industrial destruction that bombing campaigns had inflicted. But more than that, he understood the futility. Even without bombing, even with every factory intact, Germany could never have matched Allied production. The disparity was too fundamental. He thought about the Corsair, about its R-2800 engine producing 2,000 horsepower on American fuel, about Marine pilots flying combat missions from primitive Pacific islands, supported by a logistics system that could deliver spare engines faster than German factories could produce new aircraft, about the casual confidence of American pilots who knew they had performance advantages in speed, climb, acceleration, sustained power output at altitude advantages built into the fuel that powered their engines. The lesson was brutal in its simplicity. Modern wars were not won by bravery or tactical skill, though both mattered. They were won by industrial capacity, by oil wells and refineries, by chemical plants and supply ships, by the unglamorous infrastructure that enabled everything else. Germany had sent skilled pilots into combat with inadequate fuel, and no amount of courage could overcome that disadvantage. The Americans had sent adequately trained pilots into combat with superior everything, and superior fuel made every other advantage possible. That was what German intelligence had failed to grasp until too late. That was what the returning prisoners had tried to convey. That was what Ernst Richter understood, sitting in the ruins of Berlin, thinking about American aircraft he had never seen but whose capabilities had helped determine the war's outcome. The Corsairs' success in the Pacific was not primarily about aircraft design, though the design was excellent. It was about octane ratings, about chemistry, about industrial processes that transformed raw petroleum into aviation fuel that made American engines capable of performance German engines could never achieve. Number World War II Corsair script, Ter. Part 2 inches, the spring of 1946, Ernst Richter received permission to visit what remained of the Leuna synthetic fuel plant near Merseburg. It had been one of Germany's largest hydrogenation facilities, capable of producing thousands of barrels of aviation fuel daily at its peak. American bombers had attacked it repeatedly during 1944 and 1945. Richter had read the intelligence reports about these raids. He had known the plant was damaged, but seeing it in person conveyed a reality that reports could not capture. The facility sprawled across hundreds of acres. Massive distillation towers lay toppled like fallen trees. Reactor vessels had been torn open by explosions, their internal mechanisms exposed to the weather. Pipe networks that had once carried pressurized gases and liquids now dangled uselessly, severed and twisted. The plant's electrical substation was destroyed completely. The rail lines that had delivered coal and removed finished products were cratered and unusable. Richter walked through the ruins with a former plant engineer, a man named Hoffmann, who had worked at Leuna since 1939. Hoffmann explained what each section had done, how the coal had been pulverized and mixed with hydrogen under extreme pressure and temperature, how the resulting synthetic crude had been refined into various fuel grades, how additives had been blended to achieve the highest octane ratings possible with available resources. We were producing C3 fuel at 91 octane lean mixture, 100 rich mixture, Hoffmann said. It took us years to reach those numbers. We had chemists working constantly on process improvements. We knew the Americans were producing 130 octane. We knew how they did it: catalytic cracking, alkylation, aromatic compounds, tetraethyl lead. We had the knowledge. What we lacked was the infrastructure. To build facilities comparable to American refineries would have taken decades and resources we never possessed. They stood near what had been the main hydrogenation reactor. It was the size of a small building, constructed from steel that could withstand temperatures exceeding 400 degrees Celsius and pressures of 200 atmospheres. The Americans had hit it with a bomb that penetrated deep before detonating, rupturing the vessel from within. Repairs would be impossible. The entire reactor would need to be replaced, and Germany no longer had the industrial capacity to manufacture such equipment. How long would it take to rebuild this plant? Richter asked. Hoffman laughed bitterly. With what? We have no steel for new reactors, no machine tools to fabricate components, no electrical generating capacity to power the processes, no coal mining infrastructure to supply feedstock. Even if we had all of that, it would take 5 years minimum to return this plant to operation, more likely 10 years, and this is just one plant. The Allies destroyed 23 synthetic fuel facilities across Germany. The reconstruction required to restore German fuel production would exceed the entire Marshall Plan budget being discussed for European recovery. Richter understood. The bombing campaign against German synthetic fuel production had not just reduced current output, it had destroyed industrial capital that would take generations to rebuild. Germany would not produce high-octane aviation fuel again for decades. There was no point. The era of piston-engine fighters was ending. Jets and rockets represented the future of military aviation, and they ran on kerosene-based fuels that were easier to produce. The elaborate infrastructure for high-octane gasoline production was already obsolete, but the lesson remained. Wars were won by industrial capacity before they were fought on battlefields. The Americans had understood this. They had invested in petroleum infrastructure, refining technology, and chemical production. They had built an industrial base that could support total war, while simultaneously improving civilian living standards. Germany had pursued autarky, self-sufficiency, synthetic substitutes for resources it lacked. And when the test came, synthetic fuels could not compete with natural petroleum refined using advanced technology. In 1947, Richter attended a conference in Munich on aviation technology and the lessons of the war. It was organized by former Luftwaffe officers and aviation engineers, men trying to understand how Germany had lost air superiority so completely. The conference was small, attended by perhaps 50 people. The occupying powers allowed it only because the participants focused on technical matters rather than political or military strategy. One presenter, a former test pilot named Weber, gave a talk about American aircraft performance. He had flown captured American fighters during the war, a P-51 Mustang and a P-47 Thunderbolt, as part of a Luftwaffe evaluation program. His testimony was devastating in its honesty. "I have flown the FW-190 for 3 years," Weber said. "It is an excellent aircraft, well-designed, powerful, maneuverable. I understood its capabilities completely. Then I flew the P-51. On paper, the performance numbers were similar. Top speed, climb rate, service ceiling, all comparable. But in actual flight, the Mustang was superior in ways that specifications could not capture. At 20,000 feet, I could push the Mustang's throttle forward and feel continuous acceleration. The engine did not falter. It did not overheat. It simply produced power, smoothly, and reliably, at manifold pressures we would never attempt in German fighters. I flew for 30 minutes at 67 inches of mercury boost pressure, 67 inches. Our engines would destroy themselves at such settings. The Mustang operated as if this were normal cruise power." I asked the American technical officer supervising the test about this. He explained that the Mustang was designed around 130 octane fuel. Everything about the engine compression ratio, boost pressure limits, cooling requirements was optimized for that fuel. When I suggested that German fighters would perform better with similar fuel, He looked surprised. He said, "You mean you're not using 130 octane?" We assumed everyone was. The audience sat in silence. They were men who had fought the war in the air, who had lost friends, who had experienced defeat personally. Hearing that American pilots had assumed everyone possessed the same fuel advantage added another layer of humiliation to the loss. The Americans had not even recognized their advantage as significant. To them, 130 octane fuel was simply normal. Another presenter discussed the F4U Corsair's performance in the Pacific. He had reviewed captured Japanese intelligence reports that described encounters with American fighters. The Japanese, like the Germans, had initially attributed American success to superior numbers and logistics. They had believed that Japanese pilots, with their superior training and more maneuverable aircraft, could win individual engagements even when outnumbered. The Corsair had destroyed that belief. Japanese pilots reported that Corsairs could accelerate away from any Japanese fighter, that they could climb faster, that they could maintain combat power at altitudes where Japanese engines lost performance. Experienced Japanese aces who had survived years of combat fell to American pilots with only months of experience, not because of skill differences, but because the American aircraft simply performed better in every measurable way. The Corsairs R 2,800 engine produced 2,000 horsepower under normal conditions, the presenter explained. With water injection for emergency power, it could exceed 2,200 horsepower. Our Mitsubishi Kinsei engine produced at most 1,100 horsepower. The Americans had a 2-to-1 power advantage. Japanese fighters won through maneuverability. American fighters won through energy speed, climb, acceleration, and that energy advantage came from fuel that allowed engines to produce power far beyond what we could achieve. After the presentations ended, Richter spoke with several former pilots. They were bitter men, still processing the loss, still trying to understand how a military that had seemed invincible in 1940 had been defeated so completely by 1945. One pilot, a veteran of both the Eastern and Western fronts, expressed what many were thinking. "We were told we had the best aircraft in the world, the best pilots, the best training, German engineering, German discipline, German superiority. All lies. Not lies about quality. Our aircraft were well made, our pilots were skilled. But quality means nothing when the enemy has quantity and better resources. One American fighter with 130 octane fuel was worth 2 German fighters with 87 octane fuel. The Americans produced 10 fighters for every one we built. Do mathematics. We could not win." Richter returned to Berlin and resumed his civilian life. He found work as a technical translator, converting English-language engineering documents into German. Much of the material dealt with petroleum refining, chemical engineering, and industrial processes. He read about American refineries expanding production to meet peacetime demand. He read about new catalytic cracking technologies that increased yields of high-octane gasoline. He read about synthetic rubber production, synthetic lubricants, petrochemicals that were transforming industry. The Americans were not just producing more, they were innovating constantly, improving processes, and developing new products. Their petroleum industry operated as a competitive marketplace where companies invested in research and development because better technology meant higher profits. German industry had operated under state direction, producing what the government ordered, innovating only when commanded. The difference in outcomes was predictable. By 1948, Richter had accepted an offer to work for a British petroleum company establishing operations in occupied Germany. His job was to evaluate former synthetic fuel plants and determine which could be converted to other purposes. Most could not. The specialized equipment for coal hydrogenation had no other use. The facilities would be dismantled for scrap metal, the sites cleared for other development, but a few plants could be modified to produce industrial chemicals, ammonia for fertilizers, methanol for solvents, synthetic compounds for plastics and pharmaceuticals. The British company was investing in this conversion. betting that Germany's chemical industry knowledge could be preserved even as its military applications became obsolete. Richter's technical expertise made him valuable for evaluating which processes could be repurposed. He spent months visiting ruined plants, studying what remained, writing reports on salvage potential. At each site, he encountered former plant workers, engineers, and technicians trying to find employment in a destroyed economy. Many were highly educated chemists with doctorates, engineers trained at prestigious universities, men who had worked on cutting-edge industrial processes. They were unemployed because their skills served industries that no longer existed in Germany. One engineer, a man named Kruger, who had worked on C3 fuel additives, expressed the bitter irony. "We knew how to make high-octane fuel. We published papers on it before the war. German chemists were world leaders in petroleum chemistry. But we could not produce it in the quantities needed because we lacked petroleum. We had coal instead. So we built an entire industry around converting coal to fuel. Billions of Reichsmarks invested. Thousands of workers were employed. All of it became obsolete the moment American bombers destroyed the plants. They found petroleum underground and built refineries to process it efficiently. Simpler, cheaper, more effective. They won the war in their refineries before we ever fought it in the air. We lost because we made the wrong infrastructure investments 20 years before the war began. Every decision compounds. By the time we recognized the fuel gap, it was too late to close it." These conversations reinforced what Richter had concluded during the war. Military outcomes were determined by industrial foundations laid years or decades before fighting began. Germany had made strategic choices in the 1920s and 30s that created vulnerabilities the Allied powers exploited in the 1940s. No amount of tactical skill or operational brilliance could compensate for fundamental resource disadvantages. The F4U Corsair served as a symbol of these larger forces. It was an excellent aircraft, well designed and effective, but its success came from more than design. It came from an industrial system that could produce the R2800 engine in quantity, that could manufacture airframe components with precision, that could deliver spare parts to combat zones thousands of miles from factories, that could train pilots adequately, that could supply ammunition and fuel without shortage. Most critically, it came from refineries that produced 130-octane fuel that made the R2800 engine capable of performance unattainable with lower-grade fuel. Every Corsair sortie over the Pacific represented this complete system. The pilot in the cockpit was the visible element, the one who engaged enemy aircraft and dropped bombs on targets. But supporting him were thousands of workers in factories, refineries, shipyards, training facilities, petroleum engineers who designed catalytic cracking units, chemical workers who produced tetraethyl lead, refinery operators who blended fuel to precise specifications, ship crews who transported fuel across oceans, ground crews who fueled aircraft and checked for contamination, supply officers who tracked inventory and requisitioned replacements. This entire system operated smoothly because America had the industrial capacity and organizational competence to make it function. Germany had attempted to create similar systems but lacked the resource base to sustain them. By 1944, German logistics were collapsing under the strain of multi-front war, bombing campaigns, and resource exhaustion. American logistics were expanding, becoming more efficient, supporting operations across the entire globe. The war had been decided by these unglamorous factors, not by heroism, though both sides showed courage, not by tactics, though innovative commanders on both sides developed effective methods, not by technology alone, though technology mattered. The war was decided by industrial capacity, by resource access, by infrastructure that enabled everything else. And at the foundation of that infrastructure was energy, petroleum, coal, electricity that powered modern economies and modern militaries. Richter thought about this often in the years after the war. He had spent years analyzing enemy capabilities, trying to find weaknesses, recommending countermeasures. All of it had been futile because the fundamental asymmetry could not be addressed through tactical or operational changes. Germany lacked the resources to compete industrially with the Allied coalition. This was not a secret. Intelligence officers had known it. Economists had warned about it. But the regime had pursued war anyway, believing that speed and skill could overcome material disadvantages. The Corsairs' kill ratio of 11-1 against Japanese aircraft demonstrated the fallacy of that belief. Japanese pilots were skilled, experienced, and motivated. Japanese aircraft were well designed for their purposes. But skill and design could not overcome the performance advantage that American fuel provided. When a Corsair pilot could accelerate away from danger, when he could climb to advantageous altitude faster, when he could maintain combat power longer, these advantages were decisive. They were not the product of superior courage or tactics. They were the product of octane ratings, of fuel chemistry, of industrial processes that transformed petroleum into aviation gasoline. In 1952, Richter read a technical article about the F4U variant of the Corsair, the final model to see service in World War II. It had entered combat in the last months of the war in the Pacific, equipped with an upgraded R2-80018W engine and a 4-blade propeller. This variant could exceed 450 miles per hour in level flight faster than any piston-engine fighter Germany had fielded during the war. Its rate of climb exceeded 3,800 feet per minute. It could operate effectively at altitudes above 35,000 feet. These performance figures were achieved using 115-octane fuel, the 115/145 grade, that American refineries had begun producing late in the war. This fuel allowed even higher boost pressures than 130-octane, generating power outputs that approached the limits of what piston engines could survive mechanically. The F4U represented the apex of piston engine fighter design, and it was only possible because American fuel technology had advanced to enable it. Germany had never produced anything comparable. The best German fighters at war's end, late model FW 190 seconds and BF 109 seconds, could barely exceed 400 miles per hour and had service ceilings below 40,000 feet. The performance gap had grown wider as the war progressed, not narrower. American industry had improved faster than German industry could respond, and fuel technology was central to that improvement. Richter kept a photograph from the article showing an F4U 4-inches flight over the Pacific. The aircraft looked powerful, purposeful, and modern. He pinned it to the wall of his office as a reminder. Not of German defeat, he needed no reminders of that, but of the lesson the defeat had taught. Modern warfare was industrial warfare. It was won by engineers and chemists and refinery workers as much as by soldiers and pilots, perhaps more so. The side that could produce better fuel, build more aircraft, train more pilots, supply more ammunition, that side would win, regardless of individual battles or tactical innovations. The young Germans who visited his office sometimes asked about the photograph. Who had fought in fighters? Had he been a pilot? Richter would explain that he had been an intelligence officer, that he had analyzed enemy capabilities, that the Corsair represented something important about how wars were actually won. Most did not understand. They thought of war as combat, as bravery under fire, as dramatic moments that decided outcomes. They did not understand that the dramatic moments were determined by decisions made years before. In investment choices about infrastructure, in strategic priorities about resource development, in industrial policies that shaped what a nation could produce. This aircraft was dangerous, Richter would tell them, gesturing at the photograph. But not because of its guns or its armor or its pilot's skill. It was dangerous because it was fueled by 115-octane gasoline that allowed its engine to produce 2,200 horsepower. Our aircraft used 87-octane fuel and produced 1,500 horsepower. That 700 horsepower difference meant the Corsair could fly 50 miles per hour faster, could climb 1,000 feet per minute better, could accelerate away from any situation where our pilots might have gained advantage. That is what defeated us. Not courage or tactics. Chemistry, industrial capacity, resources we did not possess and could not acquire. Some understood, others did not. But Richter felt obligated to try. The war's lessons needed to be learned, remembered, passed to the next generation. Germany had lost because it had pursued a war it could not win industrially. The courage of German soldiers had been meaningless against Allied material superiority. The skill of German engineers had been neutralized by resource constraints. The propaganda about German superiority had been lies, or rather, truths applied to the wrong domain. German engineering quality meant nothing when Germany could not produce in quantity. By the late 1950s, the lesson seemed to have been learned. West Germany was rebuilding as an industrial economy focused on export manufacturing. The economic miracle, Wirtschaftswunder, was underway. German companies were producing automobiles, chemicals, machinery for international markets. But Germany was not producing synthetic fuel. That industry was dead, replaced by imports of crude oil that was refined using modern technology. Germany had learned to integrate into international trade rather than pursuing autarky. Richter retired in 1963. He had spent nearly 2 decades in the petroleum industry, working on projects that had nothing to do with military applications. He had helped build chemical plants, advised on refinery operations, consulted on petrochemical production. The work had been satisfying in its way. He was using his technical knowledge productively, contributing to economic recovery, earning a comfortable living. But he never forgot the war's lessons. He never forgot studying documents in his cramped office at Luftwaffe headquarters, realizing that German fighters were outmatched not by better design, but by better fuel. He never forgot interrogating American pilots who spoke casually about 130 octane as if it were unremarkable. He never forgot the reports from returned POWs describing American abundance that German civilians could not imagine. He never forgot standing in the ruins of Leuna synthetic fuel plant, understanding that German industrial capacity had been destroyed beyond hope of quick recovery. The F4U Corsair remained his symbol for all of this. It was not the most famous American fighter, the P-51 Mustang held that honor. It was not the most produced, the P-47 Thunderbolt exceeded it in numbers. But the Corsair represented something specific about how material advantages determined outcomes. Its success in the Pacific, its 11-to-1 kill ratio, its dominance over skilled Japanese pilots flying capable aircraft, all of this demonstrated that industrial capacity trumped individual skill when the disparity was large enough. In his final years, Richter occasionally lectured at technical universities on the history of aviation fuel development. His presentations were not about tactics or strategy. They were about chemistry, refining processes, octane ratings, and industrial infrastructure. He would show slides of refinery equipment, explain catalytic cracking and alkylation, discuss the challenges of producing high-octane fuel from coal versus petroleum. Then he would show performance data for German versus American fighters, demonstrating how fuel quality translated into combat advantage. The Americans did not win the war through better pilots, he would tell students. They won through better petroleum engineers. The octane advantage was decisive. It made their fighters faster, their bombers capable of flying higher and farther, their entire air force more effective. German pilots could not overcome this advantage through skill or courage. The performance gap was too large, and that gap existed because American refineries could produce fuel that German synthetic plants could not match. This is the lesson, he would conclude. Wars are won by industrial systems, not by warriors, by engineers who improve processes, by chemists who develop better fuels, by workers who manufacture products efficiently. The dramatic battles you read about in history books were determined by decisions made in refineries and factories, made years before fighting began. Germany lost the Second World War because it lacked petroleum and could not produce substitutes of adequate quality in sufficient quantity. Everything else followed from that fundamental resource constraint. Ernst Richter died in 1978. His obituary in the local newspaper mentioned his service in the Luftwaffe during the war, his subsequent career in the petroleum industry, and his technical contributions to German chemical production. It did not mention the F4U Corsair or his understanding of why Germany had lost. Those were private conclusions, shared with students and colleagues but not widely known. But the lesson remained. The Corsair, powered by American high-octane fuel, had helped win the Pacific War not through dramatic dogfights, though there were many, but through sustained industrial superiority. Every sortie it flew demonstrated that American refineries could produce better fuel than German synthetic plants. Every Japanese aircraft it shot down proved that resource advantages determined outcomes more surely than skill or courage. Every successful mission it completed showed that wars were won in laboratories and factories before they were fought in the sky. The photograph remained on the wall of Richter's former office, kept by the company that had employed him. A young engineer worked there now, focused on petrochemical production, with no connection to the war or understanding of why the Corsair image was significant. But it stayed, a reminder of lessons learned through defeat, that industrial capacity decided wars, that fuel quality mattered as much as aircraft design, that chemistry and engineering were more decisive than tactics and courage, that the unglamorous work of refining petroleum was worth more than the glory of aerial combat. The F4U Corsair had been retired from American service by the 1960s, replaced by jets that flew faster and higher than any piston-engine fighter could achieve, but its legacy endured. It had demonstrated decisively that modern warfare required modern industrial capacity, that resource advantages could not be overcome through skill alone, that wars were won by petroleum engineers and chemists as much as by pilots and soldiers. That was the lesson Ernst Richter had learned. That was what the Corsair represented. Not individual heroism, though there had been plenty. Not tactical innovation, though tactics mattered. But industrial reality, the simple, brutal fact that the side with better fuel, more of it, and the infrastructure to deliver it where needed would win. Everything else was detailed. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.